Hey, well, welcome back to, I guess this is week 1 and day 2. And we're working here on the first chapter. Yeah, come on in. I think there's a couple seats still here and back there and along there. But yes, we are a full class. And I think that'll work okay in the class. I'm very concerned about the labs, but went okay the first 2. We'll have the third one here this afternoon here. All right, well, let me get you started and also just kind of point at the syllabus here real quickly because, like I said, most of my classes are with the same structure, and this one has as much of the same structure that makes sense. It's just that the material and the layout's a little different, so it doesn't have that same structure. And just want to remind you then of where we are and where we're headed here. Because as I pointed out here on that first day, that we spend these first couple weeks and just right away, oops, this is the wrong class. Never mind. I have the syllabus somewhere for this class. Aha, here we go. But right away here in week number 4 on Tuesdays when we do that first test, if you will, a half test where we have 3 problems, or call it 2.5 problems, makes it a little easier. But the idea here is we're going to hit these chapters, we're going to hit them kind of fast, and you'll see here this first week we're doing chapter 15, and that's pretty normal for those of you who've had me a chapter a week. But look at next week. Look as we head into next week and you get ready here for next week. We're going to spend 1 day on chapter 16 and only 1 day on chapter 17. We probably won't do complete justice to those chapters. They might get shortchanged a little bit, but that is part of the game plan here. And I will say this, that I certainly would not test you on anything that we don't cover. And all that is to say then, I want to make sure we finish up 15, don't want to fall behind, because we only have 1 day for 16, and so we should have plenty of time to finish the material. My real question is, will I have time to do examples, as I always like to do? So that, in that sense, this first little section, these first 4 chapters that we're trying to do in 3 weeks and throw a half test in there is a little tight and maybe a little bit different here. So unlike the past one, just keep that in mind. We're probably going to go at a little faster pace. Hopefully the material isn't quite as overwhelming, so it won't feel like a faster pace. But also, I won't probably do as many as examples, and so it's just the way it'll come out. Yeah.
Preparing for class.
Yeah.
Like reading the chapters beforehand, or should we be reading the entire chapter, or can we be skipping like some chapters?
Yeah, difficult to say, because my hope and my dream, my wish list on the syllabus is that we're not going to skip any of the sections. We're going to get to them all. And the truth is, though, we'll get bogged down, and I'll have to tell you. But I won't be able to tell you to the day of the lecture, so I can't tell you ahead of time which ones not to read. Yeah. All right, so with all that said, why don't we jump in? Quick review of what we did last time. And really, what we did last time explains everything we're going to do today. And I hope that will get across to you really well here. I'm going to change pins here. That one's feeling a little dry or worn out there. But if I take then a mass M and I hook it to a spring, attach it to a wall, spring constant K, frictionless ground, and say, okay, let's write out the forces, and I guess we could say the x direction. That would give us the acceleration in the x direction. Since there's only one thing pushing or pulling it in the x direction, it's the spring, it's minus kx. That has to equal to m. We could write acceleration as the second derivative of position. Then, if you recall, we spent quite a bit of time really in a mathematical discussion about this equation. I'll put a box around it again and point out here that, okay, this is an equation. All we have to do is solve it. We didn't do anything new. We just had Newton's second law. Add up the forces. That's our net force. Set it equal to ma. And now solve the equation. And so we spent some time, and let's not repeat it again here, but let's remember the answer. What function can you take its derivative twice? Have the same function, but with a negative in front. And then maybe some constants. Answer? Yeah, and so these were our sines and cosines. So we spent a little time saying that this would be the solution to that. And we even took the derivative twice to verify that it was. And we said this thing here, what we called the omega, is then the square root of k over m. And so again, you could see it by if we then took the derivative the first time, right? That would give us velocity. We would get a negative omega, an a sine, an omega t plus phi. If we took the derivative a second time, we would get acceleration. That would give us a second omega from the chain rule. The sine would go back to cosine, and so there is our equations for position, velocity, acceleration. I think we also did a force, but I'll leave that one alone because it really just came out to be the kx. We continued this to say, okay, what would be the equation for the period, which we said comes out to be 2 pi over omega, which is 2 pi times the square root of m over k. We said what would be the frequency. The frequency is the reciprocal of the period, and that would be 1 over 2 pi times k over m, or put another way, 2 pi times the regular frequency, if you will, is equal to the angular frequency. I think we even had some other equations here. We said that the total energy is 1/2 ka squared, or the total energy is 1/2 a times its maximum speed, where the maximum speed here is the omega times the amplitude. I think we also said the potential energy from the spring at any moment would be 1/2 kx squared, where x is that number. We even said what would be the kinetic energy at any moment. Well, it would be 1/2 mv squared, where v would be that at any moment. Let's see, I think we had another one that said the equation for the velocity based on position instead of based on time would be, I'll have to think about this for a second. It must be total energy, a squared, minus potential energy. Must be an omega, like that. And where omega is a k over m. That doesn't look right. Let me think about that for a moment. 1/2 ka squared equals 1/2 mv squared plus 1/2 kx squared. So I move this over to here, get rid of the halves, I get ka squared minus k. Yeah, okay, all right, now it's looking good. Equals to v squared divided by m, and so the square root of k over m and the square root of a squared minus x squared is equal to v squared. Okay. All right, well, I'll stop there because I'm taking a little too long to kind of review these, but here's what I want you to get out of this quick review, besides a chance to review all these formulas, is do you see how this form of the equation then leads to all this? And so here's my point today. Watch what we do with a bunch of other scenarios. If we ever come up with this equation, don't we already know all the answers? And that's how we're going to do the rest of the chapter. Almost. There'll be a few other equations that are a little different from this towards the end. But right now, if I ever come up with an equation that looks like this, this would be the answer. And so I'll just leave that here on this side of the board here. I'll clear this off here. And let me just work on these two sides of the board. Let me leave that here then and say, all right, let's switch things up a little bit. Now that in the first lecture we talked about, one spring horizontally. We spent a long time talking about that. I'll change it a little bit. Let's do this. What if I were to take that same mass, okay, and hook it to not just spring number 1, but spring number 2. What happens there? And probably doesn't surprise you that I have one right here, right? Here is spring number 1. Here is spring number 2. Not necessarily identical springs. That's why I put K1 and K2. And if I take it and I pull it slightly to the right or left, your right, and let it go, does it have the same kind of motion as a single spring? Seems to look like it. What would be its period? What would be its frequency? What would be the equation for the position, the equation for the velocity, the equation for the acceleration, the equation for the maximum velocity, the equation. Can we solve that one too? And I bet we can. Watch. Let's write it out. Let's go through exactly the same thing. I'll start right here. Let's add up all the forces in the x direction. And so if I come along here and I go, all right, let's add up all the forces in the x direction, set it equal to mass times acceleration in the x direction. What would I get in this case? Well, I guess I would have a minus k1x and another minus k2x. In other words, if I move it over that way, aren't I going to get a force from each of the springs? So the net force is the two springs together, right? And so I'm going to move it over. Okay. And then that would be m, and then this would be the second derivative of the position. So again, x being that distance that I moved it over, or its position as it goes back and forth. But if you look closely at this equation, I'm hoping you will see here that this could be written as k1 plus k2 with an x, an m underneath, giving then the second derivative with respect to time. Let me stop right there. Put a little box around it here. Does that look at all familiar to anything I've already done? It does, doesn't it? I mean, if you compare the situation now with two springs compared to one spring, you're really seeing that it is going to have the same form of the equation, the same form to all the answers. The only difference is what? Yeah, the k has been added together. So I would like to put it this way. Let's call this the effective k. And even though there's really two springs, if you think of the two as combined together, then this equation is really the effective spring constant divided by m times x equaling the second derivative. And so then we could go through, and we won't. We don't need to. We could go through and solve that equation, but doesn't it have this form? So wouldn't you have exactly the same equations, just everywhere there's a k, you would replace with k1 plus k2. Mm-hmm. And do you know the period? Do you know the frequency? Do you know the position? Yes, yes, yes. Bunch of questions.
What happens if you have two springs attached to the same side of an object?
Ah, okay, let's do that next. Great question.
I just wanted to ask why it's not the difference of the two Ks, because the force is
All right, I'll answer that one first here. But before I do then, as one example, I don't want to repeat all of these because I want to show you so many other things. But I do want to show you the trick for today and for the homework is simply this. That if we set up a situation and the situation comes out to have an equation that looks like this, then we know all the answers. And we don't have to take 10, 20, 30 minutes to solve it. We already know the answer. Fair enough? And that's what you'll be asked to do on the homework also. Okay? And so as one example, if I come over here and say, okay, so what is the equation for the period of this as it goes back and forth? Well, I guess it would be 2 pi times the square root of m over k1 plus k2, right? And so there's just one example of what I could put as any of these to find out what is the period or what is the frequency. All right, a couple of really good questions. I'll start with yours that says, well, when I put these two springs together, and this is the neat thing about Hooke's law, but can be a little confusing about Hooke's law, do I subtract them or do I add them? Now remember, if I was, and maybe this will help, I'll come over here on the side, because we did a lot of this in Physics 121. If I pushed with a force F1 this way, and I pushed with a force here F2 that way, what we often did in Physics 121 is we said F1 minus F2 because they're in opposite directions. And I think that's what you're asking me. You're asking me, why don't I subtract these instead of what I really did was add the Hooke's law to it, right? And the reason we did this in Physics 121 is what we really meant is absolute value. We really meant, okay, this is the magnitude of the force, and the one's in the positive direction. And the other one is the magnitude of the force, and it's in the negative direction. That's not what we mean by Hooke's law. So let's look a little closer at Hooke's law, because I think that's where it boils down to for you. If you have just a spring here, okay, and you pull it, well, how about if I call this x equal to 0 for a moment? And we will call this the positive direction, the traditional positive direction. And if I take a spring and I pull it out to here, I think you are thinking, okay, well, there's got to be the force from the spring in the negative direction. Well, negative kx gives me a negative number because I have pulled it and the x is a positive number. And so this plus a negative kx, which is what's happening when this one gets compressed here, this one is actually a force in the negative direction, right? And this one is also a force in the negative direction. And so the sign, if you will, is accompanied in the equation. So what I really have is force 1 plus force 2, where the sign is buried, if you will, in the equation itself. Because watch the other direction. If I were to take this spring and push it this way, so the force from the spring would be that way. You would, again, expect the force to be in the positive direction. The position is negative, but the force is positive. And you'll see that in this equation. If I push this in, by putting a negative in front here, Hooke's law, I have a negative position. And so as I move the block to this side, that whole thing does correctly give the right sign because the position is negative. And this one correctly gives it also. And so that's why I just take the equation of Hooke's law and add it with the negative sign. Does that make sense? Okay. And you'll see that works with your question. Let's try another one example. It's not too much different than the two springs on the same side, on the opposite side. But let's try by hooking a mass, and we will put two springs, or 3 or 4 or 5 springs on the same side. What happens there? Right, and again, hopefully you'll see this pattern again and again for the next hour. Here's the trick. The trick is, write down Newton's second law, see what equation you get. If you get an equation that looks like this, you know these are the answers. You don't need to go through the math again. Write the answer immediately. And we will see that here for the same side. I will write the sum of the forces. So the sum of the forces on the x direction equal to ma. Let's see, what force do I get from spring number 1? It's a minus kx also. Now, you might want to take some time to think about the minus sign, but it is the same idea that if I push it in, the x is negative, giving me a negative with a negative, the force is that way. If I pull it out, then this number is positive, x is positive, and so the negative here pushes it in. So this gives me the correct direction of the force because the negative is out in front, whether or not the position is positive or negative. And the same thing can be also said about spring number 2. And even though they're on the same side, it really comes out to be the same formula. And I do agree, that seems a little weird. Yeah?
Would it change anything if the springs had a different natural length?
Oh, yeah. That is a good question because I do have to measure their force from their position. So if they had a different natural length, this second one might look something like this, K2 x plus or minus some offset. And so I would have an equation that has a this part, but then it has plus a constant over here. And I'll say, let's certainly not talk about it right now. We'll kind of talk about it on my next step, but we mostly won't do that. We'll set them up here, and we'll do that to you next semester when you get to your advanced mechanics class. Yeah. All right. So I'll erase that for now. But that's a good question. But again, my answer to you is, all right, write out the force on it. See what kind of equation you come up with. Particularly if it comes up with one that's like the one we've already solved, or maybe if it's close, you could figure out what the answer should be. All right, so let's see what I have here. Now, again, this one I'm hoping you can see it right away. It's one of the easier ones to see compared to some of the other ones we're going to do. But there is an equation that looks just like the one we had spent a lot of time on Tuesday doing. And so, do I know the, say, period again? Sure. In fact, of course, this equation looks exactly like the one where the two springs are hooked to it, but they're on the same side. So this becomes 2 pi square root of m. And I would call this the effective k, where the two together are the effective k, and that would be a k1 plus a k2. Fair enough? See the little trick? Right? See if you can write it as an effective k? Let's try this one. How about a little harder one? What if I take my wall and I hook my first spring, K1, and then hook what I will call in series a second spring, K2, and then I will hook the mass to that, and then I will pull at a distance x and let it go. All right, so imagine this being x equals to 0, and I pull it a distance x. So again, measuring x from the natural length, being you might say the total of the two springs together. Okay, so there's my x equals to 0. And so as I do my free body diagram here, and I say, all right, let's look at the forces in the direction on that object. Are both springs touching that object?
Only one spring is touching. I think they're both effectively the one spring you grab.
Told you this one was harder. You'll be surprised how easy it eventually works out. But it is harder to see here at the beginning here. So let me draw a couple pictures here. I'll start by maybe right below it drawing this picture. That if I were to look at spring number 1 here, I would say spring number 1 has extended some distance. Let me call it x1. And then spring number 2 has also extended, and here's where I want to be careful, because since spring number 2 has shifted over to here, maybe a new color would help, the natural length of spring number 2 may be here, so this distance is x number 2. Did you catch that? And I guess what I'm really trying to say here is notice x2 is not x. It is not x1.
So x is x1 plus x2.
So when I pull it, x the distance I pull it, is really how much does spring 1 and spring 2 stretch. Fair enough? And when you see that, and again, something else about equal and opposite forces, you got it. Okay? But that's two springs in series. That the total distance it moves over is actually a combination of how much did spring 1 stretch and how much did spring 2 stretch. Okay? Because as I look closely at this and say, well, now wait, let's look at forces. What's actually pulling on this block is what I would call K2 X2. Isn't it? I mean, that's the only one touching the block. But let's just, for simplicity here, say I pull it and I hold it in that spot. So if I'm holding it in that spot, that means back here, where the other side of spring number 2 is connected to spring number 1. So K1, X1 is the force from spring 1. They're in equilibrium there. And even if I start moving them, if we say, well, the connection point has 0 mass, then those two forces have to be equal. Let me just call this, say, F prime here for a second. Because really, my question for you, as you can see what I've done in the other two examples, is could I think of these two as being some kind of effective spring?
Wildly different values.
The K's might be wildly different. Sure, they might. Let's say X1 is very big and X2 is very small. Well, what that would mean is when I pull it to get the same force, spring number 1 doesn't stretch very far. That number's small, that number's big. But to get the same force then, number 2 stretches a lot because that number's small. Sure. And of course we could ask the other way, what if they were exactly the same spring? Yeah, then they stretch the same. And the distance x that you pull it is, twice as much as one spring stretching. Sure. So there's all kinds of different scenarios we can have with that. But here's what I'm getting at. This force here pulling back would be this effective spring times x. Or x is this effective force, if you will. This F prime divided by the effective spring constant. Over here, this force F prime is, how do I want to say this? F prime, I guess, is K1, I'll put it this way, K1 X1, and this is K2 X2. So as I put this together, this X is the effective force, or I shouldn't say effective force there, I should say that is the force on this block. It's also, for that matter, the force between the two springs. But if I take this X and divide it by the effective spring constant, and I take X1 and say, well, that's the force divided by how much spring constant does the first one have, and X2 is that force divided by K2, what I get is something that mathematically is different than when I had them hooked up before. Before I just added them together. Now I add up their reciprocals to get their reciprocals. It's what we would call a harmonic sum instead of a linear sum. But it certainly is that effective one. And those of you who've, I don't know if we saw any relationships like this in 121, We see it a lot in electronics from those of you who went through 122 already. Well, we see it here in our mechanics, I think, for the first time. We'll see it again in our optics. This just mathematical relationship does show up. So like I said, this is a little harder one. But do you see the game I played? The game was, what is the effective spring constant? I really have two springs, right? Can I rearrange it to get it effective? So as I do a little bit of math here, I guess I would start by getting a common denominator and then taking the reciprocal to say that the effective spring constant is of course made of those two springs, but certainly in a mathematical way that I would have never guessed off the top of my head. But that's the point. You're not supposed to guess it off the top of your head. You're supposed to just, what a beautiful moment. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena, right? And so, like I said, I don't think any of us would have guessed that that's what it comes out to be. Yet it does, as long as I start, hopefully, what was very simple, Newton's laws, and work it out. So now that I did all that, if I were to ask you, what is the equation of motion? What is the velocity? What is the acceleration? What is the period? What is the frequency? Could you write it down? Yeah, I'll write the period as one example. What would the period be? Right, I would replace this, all these equations here, with the effective spring constant. So that becomes K1, K2 over K1 plus K2, which, since this is a compound fraction, I guess I would have to write it by flipping and multiply. But there would be the period of oscillations, and I could do the frequency, and I could do the energy, and blah, 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 blah. Fair enough? Well, we've done a lot with springs. And not to say we're done with springs. You got some really interesting ones on the homework coming up. But let's shift gears a little bit. Now that we've doing springs, and you can imagine there's all kinds of different other connections we can do with our springs. We can go to 3 springs, for example. We can go some springs at an angle. You got a good homework problem like that, and an example one I'll get to. But let's do this device. How about we take a blob of mass, small enough that we can think of it as a point. Of course, we'll change that in a minute to take a mass that is spread out. We can't think of it as a point. You remember doing this in 121, right? We started the semester thinking of things as points, and then realized, well, they have size, and we had to do moments of inertia and torques. All right, so that's coming, but I'll put that aside here. Let's just start with a mass. Think of it as a point. Pull it to one side, let it go. What is its equation of position? Its equation of velocity? Its equation of acceleration? What is its potential energy? Of course, this now would be gravitational potential energy, right? What is its kinetic energy? And I should ask velocity again, because we have velocity as an equation based on position and a velocity as an equation based on time. Can I get this one? And so we call this a pendulum. Since we're thinking of it as an ideal point mass, we call this one the simple pendulum. But let's run through it. Now, we're going to have to use our symmetry thought process for the spring and extend that a little bit, because you can see that we don't really have a spring up there. And so I think maybe seeing this next little step might be a little more stretch of the imagination, but not unreasonable. And so I'll put up here, let's look at a pendulum. A simple pendulum. And so here is the ceiling or the support. In my case, it's this little copper rod I have up there on the top, and I tie a string. I'll make a little dotted line for the vertical. I'll pull it off to one side. I'll put a little M for mass. I'll put another little dotted line here to represent the arc of what's going to happen. You can see what happens here. It swings back and forth here. And just to have something to give me some measurements, I'll call this the angle theta. So as it swings back and forth, I'll call this length L. Ooh. Just going to ask myself, does your author use a little l or a big L?
Big L.
Big L, okay. So to be consistent with your author, I'll use a capital L also. You guys look like you're getting warm. I know I am. Fanny, no? That's right. All right, well, makes you feel any better. Terrible problem to be too hot in January. Southern California, huh? All right. Well, here is the physical picture here. And of course, like we've done all of our mechanics ones, let's do the free body diagram. Let's take that little mass there and say, all right, what forces are on it? Well, I think you know. Help me out though again. All right, clearly there is, I'll call it T for the tension. There is this string here. We've done that many times. What else? All right, force of gravity. And so just as we did in our mechanics, look for everything touching it, which in this case is just one thing, a string. All right, and then the force of gravity. All right, so there is my free body diagram here. Now to make it work out a little bit easier, I'm going to do this. I'm going to put a coordinate system on here. That is tilted, if you will. It's more than just tilted, though. It's actually curved a little bit. So, in other words, I'm going to just kind of call the axis as it goes along there and swings. In fact, I even have a question for you, because I've labeled it already X. Would you feel better if I called it S for arc length? Yeah? Okay, because that's often what we have done in a math class, right? Is S is the arc length as it swings along an arc. All right, so just to make it clear, I'm talking about the arc and not a linear motion here. I'll use the S. More than that, I'll just mention it so you know that's hopefully what I'm talking about there. All right, but let's do this. Let's look at the motion in the S direction. Right? Let's look at the motion along the arc. I think you can see that's what ends up happening, right? It doesn't move perpendicular to the arc unless the string breaks. But assuming the string is strong enough, the weight's not too heavy, it's not going to break in that one. So ignoring that effect, let's just say, look, it's going to swing along this direction. All right. So this side of the equation would be the second derivative of the arc length, right? Because that's how we get acceleration, right? The second derivative of the position, and the position's the arc length. Okay, so again, going back to the same stuff we have done, that's no different here, right? I mean, the notation's a little bit different, so it might be a little harder to see. But I'm just replacing the X with an S. Look at the other side of the equation. What force is in the S direction here? Ah, good. You see it. So the force of gravity can be thought of as the two components, one in the S direction and one in the Y direction, if you will. And the one I want is this one right here. Fair enough? Now remember I called this angle theta? So let's put it here in the diagram. Where would theta be? Well, I guess the theta is the angle between vertically and the string. So there's the string and there's vertical. So isn't that theta? right? And so, if that angle then is theta, doesn't look quite so well in my picture, but doesn't that mean that angle is theta? Which doesn't that mean the one I want is opposite, this force right here in the S direction is opposite of the angle theta? That's really what I'm after. So, in other words, the force is mg, but the component I want is sine theta, right? And the direction is negative. And actually, this is back to your question about sine here. If I call this a positive angle, then that is a positive and the force is in the negative direction. When it swings back the other direction, if I go ahead and call this a negative angle, then I would have a negative number here. Together with that negative means the force is positive, and that's what happens when it swings the other way, the force is that way. Fair enough? So the negative sign is valid whether it swings left or right. Okay, so that accompanies both, just like it did for Hooke's law. All right? Now, can you kind of see that this is looking a little bit like this? In fact, maybe one of the easiest steps to do is to cancel off the m. And so as you'll see here, the pendulum's a little bit different in the sense that the frequency, the period, all these wonderful equations will never have an m in them. So, if I want to know what's the period of this pendulum, does it matter how much mass I put at the end? No. And those of you who went through 102 with me, you did a lab on this, and we talked about it in the 102. We didn't prove it. This is your proof. In fact, I even said, oh, we'll probably do that when we get to Physics 123. So here we are now, and that's the proof here that the period, the frequency, has nothing to do with the mass. It's going to fall away from the equation. And you see that now. But again, this doesn't quite look like this, but it will get close. So let's keep going here. I'll start with the arc length. See, I have arc length over here, but I have angle here. Can I make arc length and angle look the same? Yeah, what's the mathematical relationship between arc length and angle there? Okay, so the arc length is L times theta, right? If we measure theta in radians, right? Okay, so keep that in mind. We're going to use radians. It's going to be an advantage. But that's no different than we did back in chapter 10 with the wheels rolling. We said, look, there would be an arc length. And so we used this formula before. And I'm going to use it now and replace S with L theta. And of course, an important reason for that is, what would you say about L? As you watch this thing swing back and forth, L is a constant, right? And so we can pull L in front of our derivatives. And now we have an equation that looks something like this. Minus G over L sine theta equals second derivative of theta. Ooh, I'm liking that. Doesn't this begin to look a little bit closer? Right? I mean, I have thetas instead of x's. Okay, fair enough, because that's kind of what I expect. It's got an angle to it instead of a position. It's got a negative. It's got some numbers out in front. The only thing is, this one says take the second derivative of the function and you get the same function back. What's this one saying? This one's saying take the second derivative and get the sine of the function back. Ooh. Let's see. I mean, last time I asked you, what function could you take its derivative twice and get it back? And you didn't take you long. You came up with sines and cosines. But if I ask you this one, what one can you take its derivative twice and you end up not just with the function, but you end up with the sine of the function? You would say? Well, if it's sine, don't I just get back to sine again? I don't get sine of the sine. Can you think of one? I'll help you out. No. None exist. Okay, so don't work too hard on it. All right. Don't get me wrong, there's other little neat techniques we can do. We're going to take the easiest technique. We're going to take a closer look at sine functions for just a moment here. Quick math review here. If I step over here on the side of the board here and say, let's look closely at a sine function again. If I were to put a graph up here and say, all right, here's theta. On the axis, I will plot sine theta. All right. Maybe I'll change colors here for clarity. But at the beginning, if I were to look at the slope of this at the beginning, right? In other words, if I take the derivative of the sine and evaluate it at 0, so derivative of sine is cosine, evaluated at 0 is 1, right? So at the beginning, this kind of follows a linear pattern, doesn't it? Now, granted, it doesn't keep doing that forever. But watch this for a moment. I'm going to make a little chart here. I'm going to say, let's look at the angle theta, and let's look at sine theta. Let's look at some small angles, like 0. And then maybe we'll just increase it a little bit, like 0.01. Maybe a little more, 0.05. Maybe a little more, 0.1. Maybe a little more, 0.2. Maybe a little more, 0.3. Maybe a little more. I'll just jump to 0.5. I wonder what that comes out to be. Well, I got a calculator here. Unfortunately, my calculator is probably in degrees mode. Yeah. Oh, no, it's not. Good. All right. So if I go sine of 0, I probably don't need a calculator from that. What do I get? Okay, 0. What if I go sine of 0.01? What do I get? 0.0099998. Isn't that pretty darn close to 0.01? You see how the angle and the sine of the angle are pretty much the same thing? That's what's meant right here, right? A straight line? Theta? So in this area, sine of theta and theta are pretty close to the same thing. Let me try a little bigger angle, 0.05. All right, so sine of 0.05. Well, I get 0.049979. Isn't that pretty close to 0.05? Not exactly, I agree, but pretty close. Let's try a little bigger angle. And you can see that as I move further along on the axis here, that it's going to get more and more off. And if I were to go all the way to here, it would be way off. So I'm not trying to say sine theta and theta are exactly the same thing everywhere, but they are for small angles. So if we're talking about something that's in here, maybe I don't need the harder equation sine theta. Maybe I can just approximate it with theta. Let's see what happens here. If I go sine of 0.1, I get 0.09983. Again, very close to 0.1. Sine of 0.2 is 0.19866. Sine of 0.3 is 0.2955, and sine of 0.5 is 0.47994. And so, even as far as a half a radian, I'm only off here by, say, 6%. I'm closer to 4.2%, right? So I'm not that far off. Now, in my own mind, I'm thinking, how much angle in degrees is a half a radian? All right, well, all right, so 0.5 times 180 divided by pi that's 29 degrees. Let's call it 30 degrees. And my point is this. If we're looking at something rocking back and forth, like this pendulum, and we're willing to say, let's do some small angles, something say no more than this, which is very reasonable, fair enough, 30 degrees, we can make an approximation and not try to solve this harder equation, but solve this equation. Did that make sense? Because why do I like that equation? Because I already solved it. Yay! And then it looks exactly what I have. It looks like, take the second derivative of a function. What do you end up with? A negative, right? And some constants. And the function back. And that's my point. That's been my point all morning and will continue to be. Write it down and find out what the effective spring constant is. So this one's a little weirder in the sense of calling it an effective spring constant. So I don't think I will or should. But you can certainly see then that if you were asked to write out the equation of motion where it says what is the angle as a function of time, could you do it? Yeah, we already did it, right? Wouldn't it be the amplitude, which you might call the, I'll just still call it amplitude, cosine of omega t plus phi, although I suppose what would be different here is what would be omega? Yeah, the square root of g over L. And if you were asked then to get the arc length, which would be the length of the pendulum times theta, you, of course, would have arc length, and maybe I should put a little theta here for the amplitude measured in radians here, and so amplitude there, and cosine, and I'll even just put in the square root of g over LT plus phi. Right? If you were asked what is the period of this, you would say it is
2 root L over G.
Yeah, and so here we want to be a little bit careful. It's not just, the effective K. We're replacing K over M with, where'd it go? Well, I guess there it is. Maybe I should have wrote it as 2 pi over omega. So when you take the reciprocal of omega there, you get an L over a G there. So again, instead of having the, did I write that right? K over N? Yeah. And then I would have an L over G. Or I could get the frequency. And the frequency would be, and maybe I better not do too much at this point, but I do want you to realize that by taking this approximation, by again starting with very simple writing out the free body diagram, I can get the equation of motion.
What do we do when it's over 30 degrees?
Well, if it's over 30 degrees, let's wait till next year. And you have completed your Math 220. For those of you who've done your 220s, there is no what we would call closed form solution, but we would just do a power series. We can write this as an infinite series. And your author used to include that in the appendix. I don't think these later editions of the book do. But he used to, include it down at the bottom. Fair enough? All right. If that made sense, let's try the next step. As you can see, to work this out, we overly simplified the real world, right? We even I shouldn't say overly simplified, but at least we simplified or approximated the math here. So let's change it. Let's get rid of what I will call the simple pendulum and get to maybe more of the real world, where what we have is something that the mass is distributed. It's not all concentrated at some point. And in my case, I just grabbed the meter stick here and said, all right, let's take the meter stick, let's pull it at some angle, let's let it rock back and forth. Could I get the equation of motion? Could I get the velocity? Could I get? I bet you can. Yeah. Nah, we'll go through it. Yeah.
Could we find the acceleration using potential energy more accurately? Beyond 30 degrees?
Well, if you're only after the acceleration, yes.
That is d squared theta dt squared.
At that moment. But if then you write out the equation, you're still going to end up with an equation like this. And so if you were to ask, could I get a more accurate equation for period? No.
We're after the period.
Yeah. But I would even argue that if you were only after the acceleration at one moment in time, you could get that exactly by leaving sine theta in here. You don't have to make this step. Right? But if you were after the equation, acceleration as it changes with time, you either have to solve this one exactly, or then you do this approximation and you get, well, what would we get for acceleration? It would be this thing twice, right? So the acceleration as a function of time means when I take this derivative twice, I get cosine. I still got my L, times the amplitude of the angle, and then I get this twice, which is G over L. Okay. And so there'd be my equation for the acceleration as a function of time, but it is an approximation to get it exactly what it is, and at one point that would not be hard because I'd have an angle at that one point. Yeah, sure. Oh yeah, I think I forgot the minus sign. Yes, thank you. Left it off to see if you were paying attention. No, obviously I did not. I got careless there. All right. Next step. So let me get the eraser. Again, I think you're seeing how the rest of this chapter plays out here, that we just kind of keep making new steps. Each new step is going to be something, that's maybe a little bit harder, maybe a little bit easier, but certainly different. And so we've got to start with our mechanics, our equations of motion, and write them out. So when we have something that looks like this, instead of calling it a simple pendulum, we call it a physical pendulum. And so there's kind of the subtlety in the words there. But if you're reading along and they want you to solve a problem and talk about a physical pendulum, what they mean is don't overly simplify it and say all the mass is at a point. The mass is spread out. I picked the meter stick because the meter stick is a really good one to clearly illustrate the mass is not at one point. The mass is clearly spread out over a long distribution. I mean, sometimes you can have things that, have a string that goes this far, and then you have a big object on it. And now you have a harder decision to make. Do I want to treat this as a physical pendulum, which would be more accurate because the mass is spread out, or do I just kind of want to squish it all down to a point and say, well, it's kind of like a simple pendulum? And it is really not. And of course, it depends on how big the mass is. If you shrink it down, the more the bigger it is, and you think of it as a simple pendulum, the more wrong it's going to be. So your best bet really is to always think of it as a physical pendulum. But of course, to do that, we're talking now things about pivoting and rotating, right? And so instead of doing Newton's laws for translational motion, we need to do Newton's laws for rotational motion. And so that's where I begin here. I say, all right, let's take then an object, which in this case would be a meter stick, and it has a center of mass somewhere. In my example, I am actually pivoting around the end point of the meter stick, but it doesn't have to be that, and it doesn't have to be a straight object. I mean, this could be something more like this, where there is, actually, let me twist it a little bit. I don't know, maybe this. And I drive a nail in it right here. So here's where I put the nail with my piece of plywood. The center of mass is, say, here. So this is straight down, and this then is off at some angle theta. And if I pull it to the side and let it go, it will rock back and forth. So again, whether I take some weird shaped object or maybe a simple object, or I think you have a homework problem that does this. You take a sphere, put a nail on the rim of it, center of mass is at the center, pull it off to the side, let it go. What is the frequency? What is the period? What is the energy? What blah, 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 right? And you pull it up. And you can see it's going to swing back and forth here. And so without worrying about the exact shape of the object yet, we know that's why we did our mechanics. So we had that moment of inertia. Remember that? It describes how easy or difficult it is to make something rotate, right? So we'll just write everything out in terms of I. Watch. If I write down Newton's second law, where it comes to a pivot or a rotation, instead of the sum of the forces, it would be the sum of the torques. Instead of ma, it would be I alpha. And so in this case, as I come over here and I look at the torque, well, oh, and I just want to make sure I use the same notation your author uses. Your author says if this is d, d being the distance from where you are pivoting to where the center of mass is, because we know at the center of mass is the effective force of gravity, mg. Now in the case of this rod, the d is obviously half of L, but it may not be that if you have something that looks like this, or some, well, this looks like d would be the radius of the object here. Okay, but I think this one illustrates it a little bit better, that d does not have to be any kind of fraction of the length. It all depends where you put the nail. I could have put the nail here, 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 right? And so there's d, and that's my point. D is that distance from the pivot to the center of mass. Because when I go to calculate the torque, we're really talking about the same thing that we just did with the simple pendulum. The amount of force restoring it back is mg sine theta. And so this torque, give myself a little bit room, would be mg sine theta and then times d. Because torque is the perpendicular force times the lever arm. Remember that? And so how much force do I have perpendicular? Well, the magnitude of the weight is mg, and sine theta is the amount restoring it. How far away is it? D. And so there is my torque. Now to get my sine straight, same thing. Let me put a negative, because again, if I pull it for a positive angle, I want my torque to restore it back. If I pull it for a negative angle, I want my torque to be the other way. And then I can set this equal to I alpha. And in place of alpha, let me just put what alpha is. Alpha is the second derivative of the angle as this thing rocks back and forth. And you can see right away that I have an equation that almost looks like this one again. Almost looks like the simple pendulum again. In fact, we're going to make the same approximation for the physical pendulum that I just did for the simple pendulum. What could I say about sine theta? Yeah, not perfect, but pretty close. As long as we're willing to keep it under 30 degrees, we're only looking at about a 4.2% error here. So I'm going to move the I over here, make the approximation for theta, and I have an equation that I'll put a box around, but doesn't that look like this equation? Exactly. And therefore, I don't need to solve this anymore. I know the answer. What is the period? What is the frequency? What is the angular frequency? I'll start with the angular frequency. The angular frequency then must be the square root of dmg over I, right? That's the omega. It's the square root of the stuff out in front. So what's the period of this physical pendulum? Well, it's 2 pi over omega. 2 pi, and then the reciprocal of omega would be the square root of I over dmg. Okay? And so that's the equation for the period. I could do the frequency, but I better not, because I already used my hour, and I want to get into some examples, but there's also some other neat things here I'd like you to see here. But I think you're seeing the game, right? Because you got some real interesting ones on the homework. Well, one of my favorite ones is they take a meter stick, they pull it to the side, they let it go, and they first ask, okay, what's the period? Well, I just did that for you. They do it to you for the book too. Then they take a spring and horizontally connect it here and say, what's the period? Can you do it? We'll see, huh? All right, but again, the picture here, or the idea here is make sure that what you want to do is write down the free, draw the free body diagram, write down the equations, and I guarantee you will see something that looks like this. Once you see something like that, you know omega. Once you know omega, you know the period, you know the frequency. That's the point of the problem. Okay? All right, well, let's do one more in this category. We'll add one more thing and then we'll be done. But something that we could look at is, what about a vertical spring? And then, what about a spring that you wind up? Well, let's start with the vertical spring. That's probably the simplest one to do here. Maybe I even should have done it earlier when I got here. But it's got a neat little subtlety in it. I'll start here and say, okay, let's look at a spring hung in the vertical direction. And it hopefully won't surprise you that it too will come out with an equation that looks a lot like this. In fact, identical to that, and that is a little bit of a surprise, but let's look it up here. All right, let me draw a couple of pictures. I'll start with a spring at its natural length. So here's a spring starting with its natural length. You might say it's extended a little bit because the spring has mass, but let's just say the spring has no mass here to begin with. Those of you who've already done the lab know that there's a part in the lab. It's kind of fun to include the mass of the spring. So this afternoon, for the other third of you, we will do that. But in class, we'll just always say our springs have no mass. We'll wait till next semester before we add any mass to them. But we'll just say, okay, no mass here. And if I then come along, and I'm going to do a little dotted line here, so this is the natural length of it. And I put a mass at the end of it, which would look something like this. That's obviously going to extend it past its natural length a little bit, and I'm calling that x naught. The reason I say that is because the third step I am going to do is then to pull it a little bit more call that x, and let it go. So I come over here, pull it a little bit more, and let it go. But again, same thing we've been doing for the last hour. Can we write out all the forces? Set it equal to ma? All right, well, we have now the force of gravity. Yesterday we called down negative. Should I continue that? Anybody want to change? Okay, I'll continue to call down negative. All right, so we got the force of gravity pulling it down. That's negative. I've got the spring. Now again, even though the spring is pulling up, the minus sign is still there to accommodate the sign, down being negative. But this would be x naught plus x equals ma. So you can see that we have the gravity and the spring. It's a little bit more complicated than we did for just the horizontal spring here yesterday, or Tuesday for you guys. But there is a little subtlety that you may not notice. What would this be right here? Right, that's 0. How do I know those two come out to be 0? Yeah, that was my whole point of hooking it up and calling that distance the point where it comes into static equilibrium. Then pull it beyond that. That's why it was nice to break those apart. So when those go away, you have minus kx equals to m times the second derivative. And then doesn't that look like this? And so again, I would say the horizontal spring and the vertical spring give me the same equation. The only slight difference between the horizontal and the vertical spring, though, is that when I'm working with a vertical spring, what I mean by x is not how far is it from its natural length, but how far is it from its equilibrium position. Fair enough? But other than that, it would have exactly the same equations because you have exactly the k and the m in front as you did for the horizontal spring. And so again, we can write down the equation for the period of the pendulum. So the fact that the spring is hanging with gravity doesn't change its period or its frequency. And that's kind of interesting to me. Until you stop and think about it. Well, that kind of makes sense because it's this initial stretching of the spring that counterbalances gravity anyways. So now it's like there's no gravity. And so no gravity, whether the spring was vertical or horizontal, would end up with the same thing. So then I'm not that surprised.
Can you explain why negative mg minus kx naught is equal to 0?
This, when you pull down, means x is a negative number. A negative and a negative make that a positive. A positive with a negative cancel. They exactly cancel because my definition of x naught is at static equilibrium. Yeah. Was that your question? Yeah. Yes, because it's static equilibrium is the short answer. Yeah. Fair enough? All right. Let's add a little more to this. Something we have not done in any of the problems we've seen so far. What if there's friction? I mean, I think it's fair to say that when I take this vertical spring here and I pull it down, it doesn't just keep going up and down forever, does it? And why not? There's air resistance, right? And there's probably some heat here with the motion of the spring. But either way, there is definitely some resistive motion. And up until this point, all these examples I have done for you have ignored any of that. That's why the answer to them were these cosinual functions that just kept saying it would go up and down forever. And that's not what happened. I'll leave it there and let it go, and I'll even maybe draw a picture on the side. This is kind of what I expect. I kind of expect this thing to go up and down and up and down and up and down and up and down and up and down, right? Now, this is going to do more oscillations than my picture shows, but it is going to eventually be losing its energy. It's losing its amplitude as it goes along. So, let's see what happens. Let's include some air friction. Now, air friction when things are moving slow. We did that in chapter 6. Anybody remember how we did air resistance? It was what? Proportional to the velocity, right? So let's include that in our equation, see what we come up with. Yeah.
So if you were to graph how much is lost on the amplitude of each
Yeah.
cycle, it would look parabolic, right?
It'll be exponential. But let's not guess, let's prove it. Right? But it'll be exponential. And maybe I shouldn't say prove it, because we're going to come up with an equation that is beyond the scope of this class. So I'll just give you the answer. But it's a great equation for you guys in 220. In fact, no doubt, if I put this on the board, damped harmonic motion, many of you will probably recognize solving these equations in your differential class, or those of you who are there now, you haven't solved it yet, but you soon will. All right? And here would be my equation. I would say the same thing as I've always been doing, write out the forces. But as that thing goes up and down, and I know I've got a vertical one there, will it be okay if I just write the force for my horizontal one? I'm not going to include the force of gravity, or should I include it and show you it cancels off again? No? Yes. How about I get rid of that one and call it a horizontal spring? How's that? Horizontal with air friction. So obviously one of the forces from the spring, but here's the part I want you to see. The other part, there's a loss of energy due to its velocity, right? That's our air friction effect, right? That's what we saw for things that are moving slow back in chapter 6. That's what you brought up there. And for anybody who might have forgotten it, that is another force. And so if I come back here and this object happens to be moving that way, there would then be some resistive force as it goes back and forth. And of course, how much resistive force, of course, depends on, say, the density of the air. Or we could change this. This could be underwater, and I would expect there to be more of a resistance underwater. Or molasses in January type thing. I mean, it would really have some resistance. So I'm just going to leave it as a general B, and B could be a small number or a big number, but there's going to be some resistive there. And then, of course, this would equal to MA. Right? Now, if we then kind of write it like we saw before, except we now have an added term, we have an equation that makes sense. It's a one step more complicated than what we saw before. In other words, what we saw before was really the special case where B equals 0, right? No resistive. Now we've put it in there. And since it has to do with velocity, that's first derivative. And so now our question changes. It is not just what function could you take its derivative twice and end up with negative of the function, which we already said were sines and cosines, but a second term where that second term is the first derivative of the function. Or you might put it this way. Between these two, there's one derivative, right? Between these two, there are two derivatives. So we already did this, right? We said if you take the derivative twice and you end up with negative of the function, what would it be? Sines and cosines. Let's try the other question here. Let's say this wasn't here. And don't think of this as a second derivative, but just think of this as one derivative from that. So what could you do? Take one derivative and end up with that same function with a negative. E to the negative x, right? So that makes me think that there should be a cosine function and a exponential. And better still, you know when you multiply two together and take its derivative, the chain rule gives you two pieces. Not chain rule, product rule gives you the two pieces, right? And sure enough, it does. So I won't take the time, like I said, it's really beyond the scope of this class to actually go through the detailed math here, but I will do this. I will give you the answer. Try this. And since we're low at time, I'm not even going to take the derivative, but I will say that if you've got some time, take the derivative of this twice. And it will work. But like I said, hopefully it's not a surprise that it's an exponential and a cosine function. Yeah.
Could you move the two negative terms over to the other side and solve it as a homogeneous second order?
Yeah, and, right, and that's the way they will explain it in your differential class. They will put everything on one side and set it equal to 0. And say, hey, this is our standard method of solving second order differential equations. And that's great when you learn how to solve them, but I think when you do that, you kind of miss where the equation came from. I mean, you learn to solve the equation, which is the whole point of the math class. But I like to leave it this way because the point of this class is to say, where does the equation come from? Right. And the equation comes from Newton's second law. That's what I want to see. So here is the forces, here is MA. Right. So when you guys have already seen it in your math class, you probably saw these over here. And you might even have wondered where the equation came from because you didn't derive it from here. But now maybe when you put the two together, you get that. Okay. Now you can see why it's called damped oscillations, because what happens then is we do have some oscillations. And the amplitude is getting lower and lower and lower. And this would be the decay of the amplitude. Right? That's the number in front of the trig function. Right? And so, like I said, we have damped harmonic motion. This is interesting because without any friction, what did we get before? Yeah, so you can kind of see what the friction is doing. The friction, or I should say resistance here, is doing two things. Number one, it's reducing the amplitude over time. But number two, it has a slight effect on the frequency. And so we kind of break these into different categories. We say, what if b over 2m squared is less than k over m? In fact, if b is 0, you can see you just get the square root of k over m. You get the same frequency we had without any resistive. But when you add a little bit of resistance here, the frequency goes down a little bit, or a lot, depending on how big b is. But if it's just a little bit of resistance here, the frequency I get now with very little resistance is really the same frequency I would get with no resistance. So if I was doing this in a vacuum without any air resistance, I would probably get the same frequency. But if my resistance gets enough, if this was underwater, I would expect it to be a little more sluggish, right? Omega to be a little bit smaller. And that's what this is saying. But as long as this number is less than that, we call this an underdamped situation. In other words, it does oscillate. And again, some of you who have done this in your math class probably have seen this word already. You say, okay, here is my underdamped. It will oscillate. I say that because what if b over 2m squared is equal to k over m? Let's say there is quite a bit of resistance. Of course, what I'm showing you is what we would call underdamped. It oscillates. But if it is what we have quite a bit here, what we're going to call critically damped, what would that look like? What does that equation say? Yeah, doesn't that just say that you have a decay to it? right? In other words, simply put, we have given it so much resistance that we have lost the ability for it to get to equilibrium, go beyond, and come back. All it does is go do-do-do-do-do-do-do to equilibrium, right? And I took it down so you guys could see better, so let me put it back up. But this is designed so you can kind of see that. This pendulum is designed with some pretty good bearings here. So if I do this, it swings back and forth really well. This is under damped. It does lots of oscillations. But if I add some resistance via this magnet, those of you who have already done 122 might remember this at the end of class, this is our electromagnetic brake. For the rest of you, I'll just say it adds some resistive effect. And what happens here is, and you can kind of see there is an interaction of the magnet. It does resist it. And so as I pull this up and let it go through,
Not even one.
that's a good picture of critically damped. And in this case, it maybe just barely comes back there, right? And of course, it only works when it's in the magnet. So if I do this, you'll see the braking effect maybe a little better, right? And so there is an example where the resistive force being proportional to the motion is quite a bit here. Of course, really not much interest for us in this class, but I might as well do the last step here. What if b over 2m squared is greater than k over m? We like to call this over damped. Yeah.
If the metal was wider on that, would it be enough to stop it from coming slightly back?
Yeah. Yeah. If I had a more, I think what you're asking really, if I had more resistance, could I get the next step, which is overly damped?
No,
Oh.
on your demonstration, it wasn't exactly critically damped because it did come back the other direction, right?
I will say yes to that, but I don't think your math teacher will, because there's a double solution to this special case that's not so obvious I didn't solve it. And what we call critically damped is if it does this or that. And so one slightly back is also a solution that in your math class you will call that critically damped. I will not. So I don't want to have you, I want you to understand the difference slightly then between what you're going to see in your math class or what you already have seen. I don't know, have you done the 220 yet? You're in it now, okay. So what you will see, yeah. Okay, but there's our, now the overly damped one, and like I said, we won't do much with it here, but it's worth saying, especially because it may not be so obvious. What happens when this number is bigger than that number? Don't you have the square root of a negative number? Can you take the square root of a negative number? Can you take the square root of negative 4? What do you get? Yeah, don't you get 2i? Where the square root of 1 times the square root of 4, and I suppose we can argue plus or minus here if you want. So if you're a little familiar with complex numbers, that's it. We invent a new number called I, which is the square root of negative 1, and now we can take square roots of negative numbers. All right, so if I take the square root, then we ask this question. What the heck would be the cosine of 2i? And without proof, if you're familiar a little bit with complex numbers, e to a complex number is a trig function. And so cosine to a plus and minus I then reduces to e to the minus 2. If we put time in here, this just becomes another exponential. The two exponentials together just make a bigger exponential. And so these things that are overly damped do not oscillate in any way. They decay exponentially, but they would take a very long time to decay because you have a decay of two functions put together instead of the critically damped where this one went away. So this is the smallest exponential you can have without any oscillations, and hence the name critically damped. These are the kind of things that in engineering we like. We want to have a shock absorber and a shock on our tire, so when we hit the pothole, the tire goes down in the pothole and comes back so that the driver doesn't go down into the pothole and back. But then as soon as that happens, we don't want it underdamped. We don't want the car to oscillate for the next mile down the road. But at the same time, we want the wheel to return into its new position because there's a pothole coming up real soon again. So we want it critically damped. And so the right amount of resistance, the right shock absorber, will get that wheel back into alignment real quickly, ready for the next pothole. And so getting it critically damped is critical. Right? And so that's one example in mechanical engineering where we want to look at it. Whereas overly damped means that there's so much resistance in that shock absorber that as the tire extends down, it doesn't really return very well. And so at the end of the pothole, it hits the step, and so then the car goes up as the road is out here. And so overly damped would be something like this. If I were to lift this up here and pour syrup all over it and let it go, we could probably watch this return in about 20 minutes back to that spot. There would be so much resistance. And so that's our three categories of what could happen here when we throw in a little bit of or a lot of resistance, depending on how much we put in here. Yeah, one more step. Yeah. Oh, yeah. Go ahead.
So then you need to get it to oscillate before it reaches the 0?
I'm not sure. I'll say yes to that. We're not going to do anything like that, but that would actually fit with your question earlier about having a second set of springs that is offset and has a different equilibrium. So you have one that returns to equilibrium and oscillates while the other one is returning. So you have one underdamped, one overly damped, and as one is going back to equilibrium, the other one is oscillating. Yeah, so we can play games with it and get whatever motion we want. Sure. All right, well, let's add one more feature to this. And that last feature would be, all right, what if in addition to having the spring, in addition to having the resistance, this object is being pushed and pulled by an external force. And so there's something working on the outside, something trying to push it. And so, as you might guess, this would be forced oscillations. You come along and you say, all right, let's put a force on it. Now, just to kind of keep the math a little bit simpler to get the idea here, let's just say this, that my force I don't know if you want to use sine or cosine. Suppose it doesn't matter. But let me just say there's some force and it goes back and forth. So in other words, I am going to give it a force in addition to the spring. It'd be like if I grab it with my hand. my hand is an external force, and I would move it down at some frequency. Of course, the spring and the resistance want to make it go up and down at a different frequency, the square root of k over m. What we're now going to call its natural frequency. So what motion do I have? Maybe you can see it a little bit better if I take it off of here and give it a force from my hand but through the spring, so I can shake it like this. And so if I shake it, it will rattle. But how will it rattle? What will be its amplitude? What will be its frequency? And so I can hold it here and shake it with a high frequency. I could hold it here and shake it with a low frequency. Or I could hold it here and shake it at the same frequency. It naturally vibrates. Don't I get different effects? Right? And you'll, again, see that in the math. Not that we'll have time to solve all the math. That's what your math class is for. But let's at least write out the equation. Because if I were doing this, I would say, okay, my first equation is the force from the spring. My second equation is the force from friction. My third equation is the force from this outside mechanism, a sinusoidal force. That has to equal to ma. So there's my Newton's laws. Add up all the forces, set it equal to ma. If I write this as its differentials, this is dx dt. This, of course, is f naught sine omega t. This is, of course, m dx dt. And there would be my differential equation. For those of you doing math, you would probably move these other two to the other side and call it an inhomogeneous equation. Yeah?
Is there any reason you changed it from cosine to sine, or just arbitrary?
Oh, it is arbitrary. Sorry. Yeah. Okay. All right. But again, without any real proof other than to tell you that if you want to give this a try and put it into here, take its second derivative twice, put it once here, and see if this will work, it will. And here is the solution. It is actually surprisingly simple. It shakes back and forth at the frequency I'm shaking it. Didn't you see that here? Right? If I was to shake this with a high frequency, didn't you see it shake with a high frequency? It was not shaking at the same frequency as this, was it? When I was shaking it at a low frequency, didn't it move with the same frequency as my hand? And so that's what I'm saying. What I'm saying here is this thing will shake at the same frequency you shake it. But what did you notice? That versus that. What did you notice when I were shaking right at its natural frequency? Right. So the big change here is that the amount of shaking, not the frequency of shaking, but the amount of shaking depends on how your frequency is. And in fact, this equation is not a simple equation. This equation would be this. What we call a Lorentz function. Probably the best way to describe it is to plot the amplitude at different frequencies. And if you look at this closely at the square root of k over m. Oh, and by the way, I guess I should emphasize, This can be confusing. This omega is the frequency I am shaking it at. Maybe I should put a prime, because I don't want you to think this omega is the square root of k over m. Now it could be the square root of k over m. Okay? And in fact, what if the frequency is the square root of k over m? What happens here? Yeah, then this term goes to 0, and that's the smallest the denominator can ever get, right? Which means that's the largest the amplitude could ever get. Did you see how high it went? How big the amplitude was when I was shaking it at what we're going to call the resonant frequency? And so when I was shaking it at low frequencies, when I was shaking it at high frequencies, my amplitude was pretty small. But when I was shaking it at its natural frequency, kind of makes sense. When I was shaking it at the frequency it wants to vibrate at, it did. And it did a lot. But any time I got off of that, it did not shake by much. Again, those of you who went through 122, you saw this when we did our electronics. We saw this with our LC circuits and our tank circuits and our resonance. And we said, look, there is a natural frequency to that. And it will respond when things are at that natural frequency. If you're higher or lower than that, it doesn't respond much. Last example, you see that with this little machine here. Here is my machine. As you will probably see, they have pendulums on them. Now these are upward pendulums instead of downward pendulums, but they do shake. If I were to stop them all from shaking here to begin with, and hold it tight into place, and pull on them, you will hopefully see that they don't have the same frequency. They don't have the same natural frequency. And so, when I shake this one, it shakes this rod. Uh-oh. There we go. Which one responds of all these other ones? It's that one. Right? If I shake this one, what other one shakes? The one with the same frequency. Because what this is trying to say is when you force something, it will respond. It will respond to that frequency. But if you're not at its natural frequency, it will respond very little. And so these other ones will shake, but very little. It's the only one that shakes a lot is the one at that same frequency. So this one makes this one shake, but not any of the others. This one here should make that one shake, but not any of those others. Yeah. Yes, thank you. And then this is the omega prime. And so this would be the natural frequency. And so when my shaking frequency equals the natural frequency, it really responds. And that's the word that we called resonance. Well, good. We did all that. I was a little concerned we would even have time for all that, let alone still having a few minutes here to pound out a couple of problems here on as examples here. So in the 20 minutes I have left, I will turn to the back here. And to be as consistently as I can, because I really think that the example ones help a lot here. Let's read some of these, and let's work them out. I'll start with number 4 if you've got your book here, yeah? I'll say kind of, sure. But waves and oscillation, I mean, the next step past oscillation is waves, and you'll see that in the next chapters. Next chapters we're going to get into waves. We're going to extend it from oscillations into waves. And then do what you're calling superpositioning. All right, well, let's look here at number 4. And like I said, do as many as we can here. But it says here, a hanging spring stretches 35 centimeters when an object of mass 450 gram hangs on it at rest. In this situation, we were going to define that as x equals to 0. So here's what it's saying. It's got a vertical spring. Here is the spring. It's got some natural length, sure. And then we come along and we hang 450 grams, and it stretches, I better go back. Was it 35 centimeters? It stretches 35 centimeters when 450 grams is hung from it, and it's just sitting there at rest. Then it says we pull it down an additional 18 centimeters and release it from rest, and it begins to oscillate without friction. What is the position, the moment 84.4 seconds later? Okay, so in other words, we pull this down 18 centimeters more. Well, it's a vertical spring, right? Do we know the equation of motion of a vertical spring? We do, don't we? X as a function of time equals what? Okay, it's the amplitude, 18 centimeters. Maybe I'll decide whether cosine or sine here for just a moment. I definitely know there's an omega t. Maybe I better deal with what goes here. Do I do cosine with a phase? Do I do sine without a phase? Do I do negative cosine? I mean, you've got a lot of choices here on how you want to write it. But if they say you pull it down, calling down negative, where does it start? Yeah, I would call this a negative cosine function with no phase. No phase. That's probably the approach I would take with it. Okay, and say, look, that's what I've done. I pulled it back. It starts down here at the bottom. If I was drawing a graph, it would start down here in the bottom and go up and down and up and down and up and down. And that's a negative cosine function. And so I like that. And in fact, what is omega again? Omega is square root of k over m. All right, do I know m? Sure, I'll put it in kilograms here for just a moment, so it'll work well with my k. Do I know k? I do, indirectly I do anyways. Isn't that what they indirectly gave me in the first step? Did you catch that part, right? They hook it here, you pull it down this far. Isn't that then at equilibrium? Isn't it at that point where mg equals k 18? Oh, no, I'm sorry. 35, thank you. 35, right? And so if I put my mass as 0.45 kilograms, I put my g as 9.8 meters per second squared. I put my distance of 0.35 meters and I get k. Then I can get the k for this situation. So 0.45 times 9.8 divided by 0.35, coming up with 12.6 newtons per meter for k. So I have k. I have k and I have n. That gives me omega. Yeah.
I noticed that the sign convention is different. Does that matter?
Sign convention, where?
You're using 35.
Oh, okay. So, yeah, because what I guess I really have is these magnitude of that equals magnitude of that. Yeah. So I mentally dropped that negative sign there.
Do we need to pay attention to that, or can we just assume that it's the magnitude?
Well, I guess there's sometimes where the negative matters, like when I was writing out the equation, because otherwise I would not have a second derivative equals negative of something. I'd have positive of something, and I'd have exponentials instead of cosines. And other times it doesn't matter, like this. It kind of depends. Are you thinking about the magnitude of the force, or are you thinking about the equation of the force? So, yes, it does matter, and that depends on the situation. So there's not a general answer I can give you. If you felt any better, I could have said back at the beginning, this was our equilibrium, so minus mg minus kx equals 0. Right? And as I rearrange it, I would have minus mg equals 2 kx, and then x goes down, so it's negative 35. That help? And then I get the same thing. Yeah.
I just wondering if it matters.
So it won't matter in terms of me giving you points. It may matter in you. Oh, okay. Setting it up. So there's K, there's M, and from that I can now get the equation of motion. And that equation of motion then would be a negative 18 centimeters times cosine of, and so there's my K, 12.6, divided by my M, 0.45. Take the square root of all of that, and 5.29 T. Right? And now the question becomes pretty easy. They just say, what is its position after 84.4 seconds? So what's the position when time equals 84.4 seconds? Well, minus 18 centimeters for its magnitude, cosine of 5.29, and I'll just leave it all in my calculator, 1.5, well, I better, it's my significant figures here, times 84.4, so times 84.4. I should verify that. Was that the time? Yeah, 84.4. Take the cosine of that answer. Confirm I am still in radians, okay. And then times a negative 18 tells me that I am at negative 15.8. So looking at this, I pulled it down. I'm not sure how many times it went up and down, but I know it's right about here. And I'm not even sure if it is here going down or here going up, but at least I know it's here. I'll need to know in a second if it's here going down or here going up, because look at the rest of this problem. The rest of this problem then says, well, there's a bunch of things. I'll skip a couple of them, but this part, it says, find the distance this object traveled. How do I do that one? Okay, good. So let's do the period, right? The period is 2 pi divided by omega. So that's 2 pi divided by the 5.29. And so that's how long it's going to take to make one oscillation. So 2 times pi divided by 5.29 is going to be 1.19 seconds. And that becomes useful because that can really tell me how many cycles did it go, right? So let's see if I can put that on here. See how many cycles I have. So I know the total time is 84.4 seconds. If I divide that by 1.9, I got 84.4 divided by 1.19, and I come up with 70.92 cycles, really. Now that tells me hopefully a lot of information. It tells me that as it started down here, it went 1, 2, 70, and almost 71, right? So it is here, going down, almost there, not quite. So how far did it travel? Well, let's do the 70, right? The 70 times is it surely went up and down 70 times. How far does it travel when it goes up and down? Well, it goes 18, 18, 18, 18. 72 centimeters, right? All right. So I've got 72 centimeters from the up and down. 70 times 72. So there's the 5,040 centimeters from going up and down. It did not quite make 71. It was shy by 2.2 centimeters, right? So let me add to this 72 minus 2.2 centimeters. Right? Didn't quite get back down to the 18, right? Shy of 2.2. So I will add another 72, but subtract off the 2.2 and come up with 5,109, or how about 10 centimeters. Right. Warning for you. We did a lot of math, I realize. But the other part of this, which in the past I've seen students struggle with, is not getting a good physical picture of what goes on. Did you see how I reasoned that out? Without a good physical picture, without going, hey, this is going up and down 70 times. One up and down time is 18 plus 18 plus 18. It was shy of that by 2 centimeters. This could have been a very difficult problem without that good, solid physical picture. And that's what I wanted you to see here. Well, let's see if I can do another one here for you. I'm wondering if I'll skip some of those other ones. I remember telling myself 63 looks good, 58 looks good. How about I quickly write out 63? How's that? And so, we didn't quite do every step in number 4. And I didn't get a chance to do any here. But you're going to do one similar to this, so I thought it would be a good one. Here it says in 63, it says a ball of mass M is connected with 2 rubber bands of length L, each under a tension of T as shown in the figure. So here's the ball mass M, and they take 2 rubber bands under tension here and pull it. And they pull them first horizontally to each side. Then in the picture, you've got some solid walls over here, and say, okay, there is my ball. Yeah.
Where did this 2.2 centimeters come from?
Oh, okay. So back here on position, if I were to label x equals to 0, I started way down here at negative 18. And it went, okay, and it stopped at a roughly negative 16, too shy of a complete cycle. So 72 would have been a complete cycle, too shy of that. Yeah. Yeah. And again, same point. See how I had to draw the picture? See how I had to see it in my head of what, you know, how'd I get the distance of it? Okay, well, 2 rubber bands of length L, tension T, as shown in the figure. The ball is then displaced a small distance y perpendicular to the length of the rubber bands. So the ball is pulled this way. And let go. Assume that the tension in the rubber bands doesn't change by much. Okay, so we'll just, tension's a constant. It's probably better described as a string. You take a string or a rope, you pull it real tight, you put something there, you pull it sideways, and you're going to watch it shake, vibrate, right? What is the frequency and period of the oscillation? Can you do this one? Well, this would be the tension, pulling it back, right? If we call this angle theta here, where we pull it sideways, we're going to pull it back, and probably with not too much of an angle. So Be prepared. Maybe we'll get a sine of an angle, and maybe we'll replace it with just the angle. Yeah. Maybe not. I don't know. But I do know that as I draw my free body diagram, if this is the tension and this is the angle T, then this force pushing it back would be T sine of theta, right? So when I go to add up the forces on this ball, then it would be a T sine theta pulling it back, and since there are two rubber bands, I would put a 2 there for twice. And then, since I'm talking about motion in the vertical here, I'm going to put a y. Or maybe this is an aerial shot, so it's back and forth. Not going to worry about the effect there of gravity. But as I pull it to the side and let it shake back and forth, this then is my equation. But also, as I look at the geometry here, doesn't sine theta equal y over L? When you pull it off here at an angle, right? This is y, this is L. And so when I put these two equations together, I get 2 times the tension. And I want to emphasize that. You see that capital T? Didn't we have another capital T all day long? Period? Okay, so careful not to mix those two. But this, as I said, the T for the tension. So this is twice the tension, y over L equals m dx dt. Oh, and I guess I better watch my sign. If I pull it down, so y is negative, then the tension is restoring it. So this is really a force that is opposite of the angle. This is a force that is up when y is negative. And when the ball goes up and y is positive, then the force is down. So I got a little negative inside there. But you can see then we have that famous differential equation, 2t over ml y with a negative in front is equal to the second derivative of y equal to t. So could you tell me everything about this? Right? You could tell me the period, you could tell me the frequency. Right? And so if I were to put the angular frequency, it would be the square root of 2t over ml. And the period then would be 2 pi over omega. So the period would be 2 pi times ml over twice the tension. And we can even do some simplifying there. And we can get the frequency, and we can get the equation of motion, and we can get the kinetic energy, and we can get the velocity, and we can get the acceleration, and, right? Again, last warning. This is the key step as you do the problems. If you do a problem that has a pendulum that is hanging and a spring that is horizontal, right? Or a ball that is rolling in a dish, write out the equations, get the equation in that form, and you know everything about it. That's why we studied that equation. Question?
That's y initial, right?
Well, no, it's y at any moment as it's moving, right? It would be true at any moment. Y would be a smaller number. The angle would be a smaller number. But it's true at any moment. That's why it works as an oscillation. If it was only true at initial, then it wouldn't be valid for an all right.